This is lecture number 4, topics thermodynamics and dynamics of materials. So till now we have discussed about many things, lot of things we have discussed, but finally we reach a point where we are discussing about different laws. But see, in examination you will get like questions related to concept mostly. Concept, some numericals. Right? Numericals will be exactly what I will discuss in the class, and concept will be also same. So I'll ask for examples rather than definition and all. I will ask you to give some examples so that I will get to know that you know the things. Whatever I am giving examples, you can write that down. If you want to give some other examples, that is also fine. It depends on you. So whatever examples I am giving, just try to understand so that you can understood the subject. Otherwise, at the end of the semester, you will not understand what is actually entropy, what is enthalpy. We will discuss about those things later. Free energy and all. So that's why I am giving a lot of examples related to metallurgical field, day-to-day life, and also physical material. I am giving some examples. Ma'am will teach you those things also. If you can correlate how thermodynamics is related to extractive, how thermodynamics is related to physical metallurgy. Okay. So if you remember, we talked about the first law. The first law of thermodynamics. What exactly the conclusion we got? It talks about energy conservation. Okay. First law always talks about energy conservation because it will not destroy. Fine. Energy conservation. It talks about energy conservation. That means energy will neither be created nor be destroyed. It can be transferred. Fine. Or it can move from one system to surrounding or surrounding system, whatever. Okay. And or in other way, if you remember, heat input will be equal to heat accumulated plus heat release. Or in simple way, heat input is equal to heat output. So suppose you are talking about any furnace, you are trying to do some chemical reactions or you are extracting metal. So this is the thing, if you remember. I have given best example of blast furnace iron making, if you remember, right? What are the heat inputs, what are the heat outputs, how it can accumulate, okay? Anyway, so let me give you another good example. There is a subject called mineral processing. It will come in the next semester. Mineral processing. Why mineral processing? Because in the real situation, we don't get metals directly from the nature. We have to extract it from ores or minerals. Right? Those are compound sections. Like for example, you want to extract metal, iron, then you have to use Fe2O3. That is hematite, if you remember. Hematite, magnetites. Those are actually compounds. Right? So that means thermodynamically, though iron is not a stable state. If iron will form iron oxide, then that is the stability. Everything wants to be stable in the nature, whatever. They always want to be stable. So that's why iron will never obtain as a iron. It will remain in form of oxides or maybe sulfides. So that's why the stability will be more. Or in other way, I can say free energy will be less. Suppose, let me give you a simple example. Suppose you have a lot of energy now. So you can run, you can walk, you can gossip with your friends, you can go for hangout and all you can do because you have a lot of energy. How you are eating food and you have a lot of energy. Right? But if you are not eating food at all, so your energy will go down, so you become stable, you cannot move there. You will stay there on. Because you don't have energy. Right? So that's why that is the concept of free energy will come. Free energy means the energy which is available to do some useful work. So if you want to go for hangout, that is one kind of useful work you are doing, for example, right? So that energy is already available, that's why you are doing that work, going for hangout. Okay. If free energy will be less, you cannot do that work. So that is called stability. So in other way, I can simply say stability means less free energy. Or free energy is actually negative. You can say negative free energy, right? So if the free energy will be in the negative direction, that means it is the stability direction. You are going towards stability in simple way. If free energy will be more, then it is instability condition. Something will happen then again because a lot of energy is available. When energy is available, some work can be done. Otherwise, you cannot do work. Okay? More free energy means instability. Very less free energy means you are moving towards stability. If it is become negative, it is more stable. So that means in other way I can say this iron oxide, hematite, if you measure the free energy, it will be less. But if you make iron, simple iron, out of it, what will happen to the free energy? Free energy will be more in that condition. That means the iron, I am talking about not process, I am talking about just simple iron. Why? Because if you allow the iron to stay like that, it is more free energy, it will automatically become again iron oxide. That's why it corroded with time. It becomes oxides again and it will follow. It becomes a reddish color, reddish brown, that is called iron oxide. Colors one, if you have studied in school, I don't know. Then it will fall down. That means again it is moving towards stability. How? Just by reducing its free energy. I am not talking about now process, I am talking about just individual material. You take iron oxide. Which one is more stable? Iron oxide is more stable compared to this iron. That's why iron is forming iron oxide. Okay. But iron oxide will never form iron automatically. You have to do some work, you have to put some energy to make it iron. Okay. You understand my point? That's why that means free energy is more in case of iron, but free energy is very less in case of iron oxide. So throughout this thermodynamics we will study about this free energy only, free energy, entropy. That's why I gave this example. It is fine at least. Okay? And free energy is denoted by G. G basically. That is actually called Gibbs free energy. And delta G means change in free energy. G and delta G. G and delta G. This is change. This is change in free energy. This is free energy. Or some people call Gibbs free energy because there was a scientist who discovered this term and concept. Gibbs. You have heard about Gibbs free. Gibbs, that is called Gibbs rule. If you have heard about it, maybe. Okay. Anyways, we will not go into that now. Let me give another example. So what I am talking about? We got minerals and ores and we got to extract metals, but we cannot do that directly. We have to remove impurities from that first, and removal of impurities from that is called mineral processing. Okay. So in technical we call it as a gangue. The technical term of impurities in the ore or mineral is called gangue. Gangue are nothing but the unwanted material. So during mineral processing we need to remove those gangues or those impurities. So that what will happen? Finally we will get a concentrate, and that concentrate we will use for metal extraction. So that means in between your mining and metal extraction there is a middle processing, that is called mineral processing. Because mining people will do mining and take out the ore and mineral from the earth crust by doing mining. Then you need to do processing of mineral processing, so that you will produce a concentrate. How? If you remove more of impurities, you are producing more concentrate. More concentrate means you are increasing the metallic part more and more. You are removing the gangue. Okay. And finally, that concentrate you will extract metals. Okay. So why I am talking about this? I can correlate with the first law of thermodynamics. How? See how you can remove the gangue. Because minerals may be very big size, some meter, 5 meter, 10 meter, or maybe 2 meter between. Big size minerals. Right. So to remove the gangue, you need to do crushing and grinding. Crushing and grinding means you want to reduce the size to small size. Okay? If you reduce the size to smaller and smaller, what will happen? How a gangue can be removed? Just imagine. Just do some test. Suppose for example, this is a big mineral. This is big mineral. Suppose maybe some meter range. You want to make it into micrometer, for example. So how you can remove the gangue from it? By crushing and grinding. See, we are crushing and grinding means size reduction. You are reducing the size to very small. Size reduction. Okay. From this to this, maybe some microns. Micron means you cannot able to see, but for explanation I am drawing. So from this to this, how you are separating the gangue or impurities? Just use your mind. Okay, let me give some visualization. For example, this is the gangue. This is the gangue. This is the gangue. Now just imagine, this is the gangue. This is the gangue, for example, or impurities. This shaded part are impurities. And this is your metal, main metallic value, or metallic oxide, for example. So this is suppose example Fe2O3, and this gangue will be, for example, SiO2, silica or alumina. So can you tell me, if you reduce the size, how you are removing the gangues? Just see. But look at the diagram. when you crush it, so automatically this will come out, right? But suppose you are considering this one, this portion for example. But when the moment you crush it, maybe this will become two parts, this part will one and this part will one. But still the gang is there. So again you crush it. So this part will move, this part will move, this part and this part will also get removed. With more reduction, more will be released, or technically called liberation. You are releasing the gang out of it. You understand my point? Because initially in case of ore and mineral, the gangs are locked with the metals or metallic part. But if you do crushing and grinding, they will become unlocked. More you do crushing and more unlock will be there. And finally you can separate them later. I am not going into details right now because you will study that. In the previous lecture, semester I taught that subject. The videos are available. Anyway, no need to look at that. Just understand first law of thermodynamics. So you want to do crushing and grinding. You want to reduce the size. So you have to do some work on it. Of course, you have to spend some electrical energy. That electrical energy will be converted into mechanical energy. Of course, some crushing, you need some crushers, grinders. So that whatever mechanical energy you are providing, output should be also same. Law of conservation of energy. Now, energy input will be energy output. So how I can justify? But the problem is this crushing and grinding is highly energy inefficient. That means whatever energy you are providing to crushing and grinding, only 1% of energy will be utilized for crushing and grinding. All the other energies, rest of energy, 98-99% will be lost during the process. So highly energy inefficient, but still we are doing. But people are doing research so that they can utilize this energy. More amount of energy can be utilized. Only, you just imagine, only 1%. So that means a lot of energy is getting lost. So I can simply write energy input, that means mechanical energy. Input will be output. Output means, suppose you are doing crushing. Crushing means, okay, fine. Can you tell me from this size to this size you are going, what happened to the surface area? It increases, decreases, remains same. Huh? Decrease. How many of you are saying decrease? You studied this in physics maybe. You may be wrong. See, don't be scared. You may be wrong. Oh, decrease. How many of you are saying it will remain the same or increase? Increase. Actually, the exact answer is increase. So you should not consider the size. You need to consider the, actually, smaller is the size, surface area is always more. That's why if you know that, for example, have you ever heard about this activated carbon? Activated carbon we used earlier in case of echo birds. You can see those tubes are made up of earlier charcoals. Charcoal is the activated carbon. Activated carbon means those are actually powder carbons. So more is the finer size, or small is the particle. Surface area will be always more. Same material, same but size different. So here that means surface area is less. Here surface area will be more. I am not going into details. How surface area is more means more number of atoms are available on the surface actually. If more number of atoms are available on the surface, that means surface area is more. So if you break the particles, so the bulk material is initially the bulk atoms are inside, but when you break it, so those are exposed to the surface. Now of course, smaller is the size, more number of atoms will be available on the surface. Like this for example. See, so in this condition, let me explain otherwise. So these are atoms, consider. So lot of atoms will be there. Like this. But which atoms are, these atoms are only exposed to the surface. These atoms. But what happened to this? They are inside, they are not exposed. But the moment you break it, so similarly what will happen? This kind of situation may arise. So here you can see all the atoms are exposed now. To the surface, everywhere. Right? So more you expose the atoms to the surface. Oh, yeah. Concentration will never change. Concentration is what you are talking about.
In that particular area, the number of atoms will be
you can say like that. Did you understand? Initially only this number of atoms are exposed to the surface. They can take part in the chemical reaction, whatever. or to the atmosphere. But if you break it, all atoms will come out and they will expose to the surface. So that means surface area is increasing. And if you know, for better chemical reaction, we need always higher surface area. Chemical reaction will be better because they will interact with the other chemicals. Because these atoms cannot directly interact with the chemicals, no? Because they are inside. Only these atoms can be. But the moment you break it to fines, they can easily react. Okay, I am not going into much more. So what I mean to say is, so mechanical energy input will be equal to new surface area created plus, so this is actually one kind of energy. This energy will be stored in the material during crushing and grinding. Because you are creating, this see, you are doing crushing and grinding, that means you are creating more surface area, I told no. Because size becomes smaller, surface area increases. That means you are creating actually more surface area. So that means the energy which you have spent during crushing, that will be stored as a new surface energy. So the energy will be stored, this energy will be stored in those materials. Plus, you will have what? Sound pollution, of course, or noise, you can say. During crushing, a lot of noise will come out. That is one form of energy. And also, heat will evolve. Lot of heat will generate. Your machines will warm up, so they need cooling actually. You understand my point? So whatever heat energy you have input, that will be again, that means it talk about conservation of energy. So this energy utilized in crushing and grinding to reduce the size, and some of energy will move into sound and heat. So energy is conserved. Whatever energy you provided, they have been conserved. Okay. That means conserved means they have transferred to another form. You have provided mechanical energy, or you have started with electrical. It become mechanical. This mechanical energy should be used for crushing and grinding. That is a mechanical process. But some of the energy is transferred to another form, heat and sound. Okay. So there is no loss of energy actually. All the energy is conserved. Whatever. Okay, you understand my point? So this much energy is actually 1%. Only this is 1%. And this sound and heat will be generated due to friction, due to some plastic deformation, due to elastic deformation, due to movement of the materials and all. We are not going into details right now. So you can correlate how first law justifies. Energy can neither be created nor be destroyed. It can be transferred to another form. It will not lost to anywhere. Is it okay? So this is another example. Real situation. Okay, next. Yeah, second law of thermodynamics. So you may get a question from this second law of thermodynamics. If you remember, we talked about spontaneous process. We talked about irreversibility, reversibility. So that concept will be replaced. See, I have written from second law of thermodynamics talk about directionality. Suppose a process is happening, what is the direction of that process? Suppose a natural process is occurring, for example. And natural occurring process are what? Spontaneous always. You don't spontaneous. Anybody remember what exactly? Can you tell me from the last one? I can't answer. What is the meaning of spontaneous process? Don't be scared. Just whatever you know. What is the meaning of spontaneous process? I don't need any definition. Just tell me in simple words. What is a spontaneous process? Yeah, without any external energy input. Okay, very good. Very simple thing. Spontaneous means it will automatically occur by itself. You do not have to add any kind of energy from outside. Outside intervention is not required. Automatically it will happen. Bending of eyesight road if you remember. Anyway. And irreversibility if you remember? No, irreversibility, not reversible. Once the process has happened, and if you want to reverse it, it will never come back to its complete original state. Never come into original state. Some loss will be there, or some changes will be there definitely in the universe. Give an example of sunlight coming and melting your snow, if you remember. Some change will be there in the universe because surrounding, you cannot send back all the energy again into the sun. Whatever it lost, it lost. Okay, this is the best example. So directionality means how directionality? Because heat always flows